Hey, good afternoon, everybody. So I think we paused somewhere here in the last class. We were looking at situations where you couple two oscillators with very different frequencies. If you couple them using real coupling or even complex coupling, so let's take real coupling and consider the different ratios of frequencies, omega 1, omega 2, and different coupling strings. We have very complex dynamics, which is captured by this Arnold tongue map. So we discussed that in the last class. So that is of no use because you cannot. It's very hard to make such a network work and develop whole brain models and so on and so forth. So what we said is we want something like this. That is when two oscillators are coupled and if their frequencies are omega 1, omega 2 or angular velocities, then we want something like the normalized phase difference psi defined as theta 1 by omega 1 minus theta 2 by omega 2. This should be constant or this should go to a desired value. Whatever we specify, it should go to that. Just like with complex coupling, we found that with complex coupling, the angle of the complex coupling will be equal to the phase difference when the frequencies are the same. Similarly, when the frequencies are not the same, we want the nominal phase difference to go to a desired value, which should be related to the angle of the coupling. So how do we do that? We said there is something called power coupling. It's an interesting trick, which is possible only because we are using complex variable formulation. And to achieve that, we basically need to do this. That is, let's say I have an oscillator which receives input from two other oscillators. All three frequencies are different. But what happens is when this oscillator sends an input, which is high frequency output, to this oscillator, at the synapse, it gets converted into the native frequency of this oscillator. Similarly, here also, this is a low frequency output. At the synapse, it gets converted into the frequency of this receiving oscillator. So it's something like translation. So suppose two people are talking to each other. They understand different languages, but there's a device which translates the language of one into the other, and so they don't have to learn the other person's language, right? They can talk whatever they can, whatever they are talking, but the machine will do there's a connection which does the translation. So how do you transform the frequency like this into that of the target? So it requires a very simple step, right? If you are using complex variables, suppose this Z1, right, is oscillating at omega 1. So the state can be represented as A1 into e power I omega 1 t. Then if you just raise it to the power omega 2 by omega 1, right, then it, simple algebra, you get A1 into e power I omega 2 t. Okay, so you can convert an oscillation at omega 1 into oscillation at omega 2 simply by raising that complex variable to a real power omega 2 by omega 1, the frequency ratio. So in this sense, that's what we call power coupling, because a coupling where you have a power term, right? The oscillation frequency goes into the power, into the exponent. So by this method, if you want to couple two oscillators, so I have Z1 here, the oscillator 1, whose state is Z1, and frequency is omega 1. So at the connection from 1 to 2, you have the weight W12. Right, and so normally you have W12 times Z1. That will be the term that shows up in the equation of the Z2 dynamics. Instead of that, here we have W12 times Z1 power omega 2 by omega 1. So we use this strange power in a power term, Z1 raised to a power. This term is used in the dynamics of the second oscillator. So we'll see the equations in a moment. So because of this power term, right, the frequency of Z1 omega 1 gets transformed to omega 2, and that's what is transmitted to the second oscillator. Similarly, in the reverse direction, the omega 2 is converted to omega 1 by raising Z2 to the power omega 1 by omega 2 multiplied by a factor from W12, and that's what goes to the other side. So each oscillator is not, unlike in the real coupling, right, or normal coupling, not power coupling. Each oscillator here is not trying to reach out to the other oscillation or the other oscillator and come to some common frequency or frequencies with integral ratio and so on and so forth. Nothing like that. Each oscillator will perfectly oscillate its own native frequency, but the connection will make sure that what the one oscillator is saying is understood by the other oscillator. Okay, so which is a very interesting situation. And this is possible because of this special step, this term. Now, the power coupling is intuitively interesting, but what kind of a mathematical results can we get? Okay, so that we can show using very simple algebra here. Let's take two oscillators coupled through power coupling. So Z1 dot is all this, mu is the root mu will be the radius of the limit cycle, where the limit, right, of Z1 and Z2. Then I have I omega 1 Z1 term, and this is the power coupling term coming from the other oscillator. So Z2 power omega 1 by omega 2 times. So notice this coupling term. It is not simply, the two are not simply complex conjugates, they're actually different. So look at that. The strength, the amplitude, the magnitude of the coupling constant is same because it's a complex number. That is same. A is same here and here. But the exponential term e power I phi by omega 2 is what you have here, and I phi by omega 1 is what you have here. Okay, you need this special structure, right, for the coupling constant also. Only then you have very nice mathematical result. So let us see what are those. So we know how to split this into polar coordinates into R1 and theta 1, R2 and theta 2. So like we have done it before. So what we'll do now is we'll ignore the R1 and R2 dynamics because R1 dynamics is somewhat simple. And especially if you assume that the coupling constant is small, the magnitude of it is small, then R1 will simply tend to approximately root mu and R2 also will tend to root mu. So that is nothing very interesting. But if you look at the theta dynamics, theta 1 dot is equal to omega 1, right, plus this whole thing A into R2 power. Right now the power, the frequency ratio shows up as power of R2 by R1 times sine of omega 1, and this whole thing is in brackets. Theta 2 by omega 2 minus theta 1 by omega 1 plus phi by omega 1 omega 2. Right, similarly in the second equation, theta 2 dot is equal to omega 2 plus A into R1 power omega 2 by omega 1 by R2 times sine omega 2 into theta 1 by omega 1 minus theta 2 omega 2 minus phi by omega 1 omega 2. So note that in both these terms, you have a common term, right, which is this part. This part is the same, but there is an opposite sign. So we call this the normalized phase difference, theta 1 by omega 1 minus theta 2 by omega 2. So therefore, psi dot is equal to theta 1 dot by omega 1 minus theta 2 dot by omega 2. So if you plug theta 1 dot, theta 2 dot in this equation, then you get, right, and then subtraction. So if you divide this by omega 1, divide this by omega 2, you will have 1 here and 1 here. If you subtract, that disappears. And therefore, psi dot is equal to this whole thing plus this whole thing. So notice now that psi, right, so here you have sine of omega 1 times, look at the term in the brackets, you will have same term. Phi by omega 1 omega 2 minus psi, and phi by this term is the same. So if you are looking at a steady state normalized phase difference, alright, that is where psi dot is equal to 0, then this whole thing has to be 0. And that is a very simple solution, which is nothing but this becoming equal to 0. Right, so there should be 0. What that means is psi is equal to, so is defined as theta 1 by omega 1 and theta 2 by omega 2, which is equal to phi by omega 1 omega 2. Now phi is this angle which shows up. Okay, and also note that it has a very special form. The complex coupling coefficient for the first equation has in the exponential phi by omega 2, and here you have phi by omega 1. You need that kind of a special structure so as to get this simple form at the end. So if you solve this with a very simple solution, if this normalized phase difference should be equal to phi by omega 1 omega 2. If that happens, you'll have a stable normalized phase difference, and we have achieved our goal. So you can see that here you look at this term called sigma, which is basically this normalized phase difference minus this. So that should go to 0. So you define that as sigma, and run the program for two oscillators. So you can see that sigma goes to 0. So this is for the omega 1 is 5, omega 2 is 10, and A12 and A21 are small numbers, small magnitude, and phi is so many radians, right? And so you get this result. So it's working. But there are small problems with this also. That is, so sigma will be equal to 0. That is a stable state. But even when you take other quantities, like when sigma SS is 2 pi n1 by omega 1 or 2 pi n2 by omega 2. So these two should be the same. If that is the case, then what happens is if sigma is 2 pi n1 by omega 1, so that is you plug this in here. This is 2 pi n1 by omega 1. So when omega 1 gets cancelled, we have 2 pi n1, where n1 is an integer. So this becomes 0. So similarly, imagine that second term is 2 pi n2 by omega 2. Okay, so that means both should be the same. And omega 2 gets cancelled, and here you have 2 pi n2. So this is also 0. So that kind of sigma also satisfies the equation, and that is not the same as simply becoming equal to so that's not becoming equal to 0. So you have sigma equal to non-zero solutions, right? Which can also satisfy the same equation. That is a problem. So there is a space where you have the correct kind of solution, but there are also spaces where you have some kind of a spurious solutions, and you can't help it. I mean, a large network like this, if you take, you'll have some space in the state space where you have desired solution, but you will also have spurious attractors. We'll see more of this in another neural network model called the Hopf network. So this is a standard problem. But anyway, so if your initial state is close to this state, right? Hopefully, I mean, then it'll just land there and stay there. Now, so that is how you can achieve what we have set out to achieve. That is, how do you achieve a normalized phase difference, which is equal to a desired value that you can do with a pair of coupled complex oscillators by using a special kind of coupling called power coupling. Now, first of all, okay, power coupling is interesting mathematically, but I mean, it seems somewhat too artificial, too contrived. But mathematically, it may be curious. But how is it biologically valid? So biologically also, it seems to be valid. So let us present some arguments to that end. So if you look at the, let's say I have two neurons here, and there's a synapse coupling the two neurons. This is the presynaptic neuron, this is a postsynaptic neuron. And I'm measuring the activity of the presynaptic and postsynaptic neurons. So the presynaptic neuron happens to fire at a higher frequency, postsynaptic at a lower frequency. Now imagine that I have a whole bunch of presynaptic neurons like this, and a whole bunch of postsynaptic neurons like this. And assume there is a kind of a small jitter among them so that they're not perfectly synchronized. Okay, but there's only small jitter. Then if you add up the activities of all these fellows, right, and so that will be like your LFP, right, and look at the activity, it will look like a smoother sinusoidal kind of a signal, okay, which is roughly related to this frequency, this this high frequency. Similarly, if you add up the activities of all the second set of neurons, right, and you will get a low frequency term, kind of a low frequency LFP signal. All right, so basically what is happening is, and imagine that these two pools of neurons are coupled, right, in two directions. So then at the connection, this high frequency coming from here is transformed into a low frequency signal, which is the operating frequency of this pool of neurons. So in principle, that kind of a transformation is possible. I mean, that's happening all the time in the synapse. So each neuron can have its own native frequency of firing, right? And at the synapse, basically, what the synapse does is integrate all these action potentials into the EPF, right? The postsynaptic potential (PSP), right, of the postsynaptic neuron or terminal. And that PSP is integrated again when it goes to the soma. It is converted into a certain frequency of action potentials, and whose frequency depends on the local properties of the tissue here, depending upon the number of sodium potassium channels, the integration time constant, the RC constant of the membrane, and all these things. Okay, so this kind of scenario is quite possible, and this is what the power coupling takes its justification from. Okay, so we have also already talked about frequency tracking. That is, when I give an oscillator input to an oscillator, right? What happens to the output, and how to change the frequency of the oscillator. We have already seen that. I'll skip this. So what do we have now? So far, we have a network of oscillators, right? And so we have looked at how you can construct a pair of oscillators, and by extension, we can also couple a network of such oscillators. where every pair is coupled by power coupling. So there is this exactly same rules are followed to couple all the oscillators into a network of n oscillators. So then each oscillator will be producing a signal of frequency omega, its own frequency omega I. Now, by adding up all those oscillations with some coefficients, right, can we do some kind of a Fourier transform, right, or a Fourier like decomposition of an arbitrary signal and model any signal? Can we learn any signal? Can we make this network learn any signal by achieving some kind of a Fourier like decomposition of the signal of the frequency components of the signal, right, and then summing up the outputs of the oscillators? So this is basically the idea. So we can show that it is quite possible. Let us see how it works. So this network has a hidden layer, or you can call it a reservoir of oscillators. And people use the term reservoir in other contexts where you have a network of neurons which are coupled among themselves, and the whole network can produce very complex dynamics. So such networks are described as reservoirs. Okay, so we have a reservoir of oscillators with all the couples and coupling constants among themselves, and that is given by the equation. So this part of the equation is oscillation and dynamics of this oscillator, the ith oscillator, and this summation comes from the inputs of all the other oscillators into this ith oscillator. So that is Aij is a coupling constant. Usually it is a small number, positive number, and then the exponent has e power I. Phi ij is the some kind of phase difference between ith and jth oscillator. It's not exactly phase difference, but there is a kind of an angle parameter that defines the relationship between the ith and jth oscillator, divided by omega j. Omega j is the frequency of the oscillator from which this input is coming. Okay, and then multiplied by zj, which is the state of the jth oscillator, raised to the power omega I by omega j. Omega j is the native frequency of this oscillator, and omega is the native frequency of this oscillator. Okay, so that is how the Z dynamics looks. And then if you look at the corresponding theta dynamics, because like I said, the R dynamics is generally very simple. R simply tries to go to root mu, assuming that this coupling constants are small in magnitude. It is theta dynamics which is very interesting. So let us look at theta dynamics. Theta I dot, theta j dot is equal to omega j plus ajk sine omega j times this whole thing. So this term is very interesting. This is similar to what we have seen before. So this is like the normalized phase difference psi. I'll call this psi kj. Okay, then so this is psi jk minus. Okay, so and then you have another. The constant term is phi, which is the term here, right? Jk by omega j omega k. Then there's an error term. So basically, what is happening here is all these oscillators, outputs of them, are passed through weights alpha I, and alpha I are complex numbers. Okay, so they are complex numbers, and the sum of all that, you take a real part of that, and you take the output, and that you compare with this P teach is a teaching signal. So this is the desired output. This is what we want the network output to look like. So take a difference of that P teach minus the st. The difference is error term, which is this error is fed back into all these oscillators. Okay, so that is what you see here, and that has to be multiplied by sine theta j. Now the frequencies are trained by this equation. So we have seen the single frequency training equation before. That is for a single oscillator. That single oscillator to enable it to track the input frequency because of the input signal. But this is the frequency update when the oscillator is a part of a network. So it uses the error feedback to update itself, and this is multiplied by sine theta j. The output st, right, is nothing but the linear sum of all these oscillations. So here note that the output of this is of a given oscillator is Zj. Okay, so we are taking simply in this case alphas are real, so alphas are real, and you multiply that with cos theta j. So I'm ignoring the R value because R simply goes to mu, so I'm ignoring that. and someone taking this simple summation of cos theta j's, linear sum of cos theta j weighted by alpha j's. So this is output signal. So let us see what happens when we train in a network like this. So we are taking a simple synthetic signal, the PT, which is made up of three terms, right? And the A1 cos, etc., A2 cos, etc., A3 cos, etc., where A1, A2, A3 are given here, and omega 1 is 3, omega 2 is 7, omega 3 is 11. So note that they're not harmonics of some fundamental frequency, they're totally incommensurate, so totally different frequencies. And then the phase difference also totally arbitrary values. Okay. Then to train this, we are taking a network of 25 oscillators. Right. So this is the number of oscillators, and this is the learning rate for the omega frequencies, and alpha j's are initially kept constant 0.2. So what we are doing in this slide is, so this training is done in two stages. First, we train only the omegas, right? So we need to train the frequency of the oscillators, because initially the frequency of the oscillators are all random, and we train it on the target signal PT, so that the oscillators first learn the underlying frequencies of PT, right? And the problem is we have to first train the omegas and then train alphas, because if we train them together, omegas won't learn well. And why is that? Because suppose I have some oscillator here which has some omega, let's say omega k, and that happens to be a wrong omega because the frequency doesn't show up in the PT signal. But suppose the output alpha k, which ends up training itself in such a way that alpha k is equal to 0 or a small value, then so if the output weight is 0, then this oscillator will become invisible. It will never show up, and it will never show up in the ST signal. So it will never get a chance to change itself, right? So thing is, this alpha can eclipse the effect of this oscillator. So therefore, to prevent that and to make sure that all the frequencies are trained properly, we need to first have a training stage where alphas are constant and there's some small positive value. Then you train only omega, so that the omegas will adjust themselves in such a way that they track the frequencies contained in the PT signal. So that's what we are doing here. Alpha j's are constants, 0.2. You train only omegas. You have 25 oscillators. If you do that, this is a histogram of the frequencies, right, of the oscillators in the initial state. Okay, this is how they are initialized. But then you start training omegas. So at the end of training, you see that all the so frequencies have come to come to the three peaks. Right, they're all constant. So all the oscillators have now come together and got concentrated near three frequencies, which is 3 and 7 and 11. Okay, and that happens to be the omega values 3, 7, and 11. Okay, so this is a radial frequency, not hertz, right? And so this is the PT signal, which is this signal as sum of three sinusoids. So like that, in the first stage training, you have to learn only the frequencies. Then you train the weights, right? The lateral connections and also alphas. Okay, so lateral connections are trained like this. So the lateral connections are WIJs, and WIJ, let us imagine it has a magnitude term and a phase term. So how do you train that? So the equations are like this. This is the equation for the magnitude term. So here also you have the error term, right, multiplied by cosine, and here also your error term multiplied by sine. So derivations of all this is quite complicated. I'm skipping that. Right, so if you train the lateral connections and also the forward connections, I think I've shown you before. The alpha training. Okay, so alpha training is very simple. It follows delta rule. Okay, I haven't covered delta rule. Okay, I'll present it later. But so if you do that, right, you can see here that The network learns the output signals very well. So in this case, we have two outputs, again, simple synthetic signals with multiple frequency components. So you see that the network output and the desired signal are almost overlapping. So it's learned it so well. So in the second case only you can see some deviations here and there, but otherwise the first case it's almost the two are identical. So it learns very well. So now can we use such a network to model brain dynamics at a large scale? Right, because one way to measure brain dynamics, there are many different technologies, many different tools, but one way to measure it is simply using EEG or electroencephalogram. So electroencephalogram, in EEG, you put electrodes on the surface of the brain, on the surface of the head, on the skull, and measure the electrical activity of the underlying neural tissue. Right, and this is the placement of the simple, 19 electrode classical EEG. So just as in the previous case, we have trained the network to produce multiple outputs. Here it's only two outputs. Why not train a network to produce as multiple outputs, various EEG electrodes, right, or EEG signals? So when we do that, so basically this is the brain, right, and there are lots of neurons here. You think of them as oscillators. And you have these electrodes on the surface of the head, and each of them produces, records some signal. So all these oscillators can be thought of as a network. This whole brain can be thought of as a network of oscillators. So we basically have to create, right, a network of such oscillators, and which will predict then a bunch of output signals, and these are the EEG signals. And then this will be like the model of the entire brain. So that's what we're trying to do here. So you think of the brain as a network of oscillators, and these oscillators now can be passed through a bunch of weights, and they'll predict or model the EEG signals. So we have this. So it's quite a difficult exercise in practical terms, because if you look at, if you really want to have a serious brain model, we should take then high density EEG recordings, where number of EEG electrodes could be like even 2 to 6 and 512 and so on. And also, if you want the network to be a more realistic representation of the brain dynamics, then we want to take a few hundred or a few thousand oscillators, right, for the whole brain. Right, it becomes practically it's a slightly difficult problem, but in principle it is not a very hard problem. Right, so we have taken a smaller version of that. We have just trained this network to produce and model 6 EEG signals. So in each of, you can see the 6 EEG, 1, 2, 3, 4, 5, 6, and you see that in each plot, on the upper part, in the upper panel, you see the raw signal, EEG, and the network estimate. In the lower panel, you see the frequency spectrum of both signals, the original signal and the network estimate. See that in all the cases, the two are matching very well. So just 6 signals. Now we are trying to do the same thing with a much larger number of electrodes. About 64 electrode data we have now, and we are trying to train a much larger network to model that. And also you can expect a simple result, that is a simple relationship between number of oscillators and the accuracy of the fit, because the more the oscillators, the more accurate is the fit. So we can see that in this plot. So the number of oscillators is in the x-axis, and the error, right, the RMS error is in the y-axis. So you see that as you increase the number of oscillators, error goes down. Now, several future projects are going on. So this is a huge area of work. I'll explain why it is a huge area of work. So one thing is, there is now a lot of effort worldwide in many centers to create large-scale models of brain dynamics. Okay, so there's a project called The Virtual Brain, also called TVB, which is run by a center in Paris, a university in Paris. So where they are taking a network of Wilson-Cowan oscillators. So the thing is, we didn't study Wilson-Cowan, I just mentioned it once, but it is similar to your Fujimoto and Morris-Lecar kind of oscillator models. So this is what they're using. They're using actually many different oscillators, but prominently they have been using Wilson-Cowan oscillators. So you take a network of such oscillators, right, and then you make it predict the brain dynamics as it is recorded from, say, fMRI or bold signal. right? Blood oxygen level dependent signal. So the only thing is we are also doing something similar, but thing is in our case we have learning equations that tell you how to modify the frequencies, how to modify the lateral connections, and how to modify the forward connections, right? And in fact, I didn't go through that, but even these learning rules, for example, how to modify the lateral connections, can be connected to some kind of complex version of Hebbian learning, which is a well-known form of learning seen in real synapses. I'll discuss all that later on in the course. So our learning algorithm is, biologically quite interesting. But whereas in this case, they just fix the frequencies, right, of the oscillators, and they train the connections. They don't train the connections. They pose the whole thing as a very complex, multidimensional optimization problem, and simply optimize all the connections so that the network of all these oscillators will be able to produce and or reconstruct the time series signals that is recorded by fMRI. They've also done similar work with EEG and MEG. MEG stands for magnetoencephalogram, which is also like a one way of measuring brain dynamics. Okay, so we want to do a similar exercise, but using our network of oscillators. So where we model the brain as a huge network of HOPF oscillators and use our power coupling and all the learning equations that I mentioned, right? And then try to model EEG data or fMRI data. So this is what we are, aiming for over the next year or so. So one more project we are very excited about is to create something called tonotopic map, right? Using the same oscillator network, network of HOPF oscillators. Now, so tonotopic map is basically a kind of a map that is observed in real brains. It's a map of sounds. So this kind of a nice map of frequencies is found in the auditory cortices of real brains in many animal species and even humans. Only thing is, in humans, the map can be quite complicated, but in certain animals, it is very simple in structure. So the idea is in this map, it will consist of a two-dimensional array of oscillators, where in one dimension, the frequency is mapped, another dimension, phase is mapped. So why is it like that? Because if you want to model a signal, we know from our understanding of Fourier series that you need to have a bunch of sinusoids, right, which take care of two parameters. One is the frequency, right, all these harmonics of the fundamental, right, m omega t, right, and so I mean in this case omega naught is taken to be 1, right, as without loss of generality, or you have okay 1 by t is a frequency, and and the other thing is phase. So the phase here, because you have a cos and a sine term, they have like the 90 degrees off. Or if you take the two coefficients of the cos and sine term, you can express a pair of cos and sine terms into only cosine with a constant phase, right? So basically, if you want to express an arbitrary signal, you need to find out the corresponding frequencies and the phases. Okay, so you can think of this whole thing as an array of so you have frequency mapped in one area, and you have phase, right, which is encoded in like AM, and BN. Okay, so like that, we want to generalize here. Is normally in a Fourier series you have only two phases, or you have only one phase captured by a cos and a sine. But you can have more sinusoids, and that will just be redundant representation of phase. So which is what we are planning. We want to have in this array of oscillators. Now, to do that, HOPF oscillator is a great oscillator model to achieve that, because one property of HOPF oscillator which I didn't discuss before is it exhibits resonance, right? Which means if you take a HOPF oscillator with intrinsic frequency omega naught and present a complex sinusoid f into e power I omega t of intrinsic frequency or frequency omega, then when you present this and assume that this capital omega is difference between omega and omega naught. So assume that the input frequency omega is quite close to the intrinsic frequency of the oscillator, right? How close is quite close? I'll explain in a moment. So if that happens, then the output will also be a sinusoid, and the output frequency will be omega. So that means the oscillator will follow the input frequency and not exhibit its own intrinsic frequency omega naught. Okay, which is a nice property. And not only that, and so this plot, right? I'm not going to the underlying equations, but this plot represents the magnitude of the oscillator response. That is mod of this whole thing. Okay, so right is equal to as a function of this frequency difference, omega minus omega naught. If we do that up to about this point, this here and this here, right, output will have the same frequency as the input, right, irrespective of the intrinsic frequency of the oscillator. And that magnitude will have a nice bell curve, or some kind of a Gaussian-like shape, which indicates that when the two frequencies are the same, input frequency is same as oscillator frequency, oscillator responds with a high amplitude response. But as input deviates from the native frequency of the oscillator, response goes down. So basically, the oscillator resonates with the input frequency. So that is very important, because if I want to have a map of frequencies, and if I have 2D array like this, right, if I give some input frequency f into e power I omega t, the same frequency input is presented to all the oscillators, right? Then depending upon whichever is the oscillator which has those frequencies closest to the frequency of the input, that oscillator should have highest response, right, compared to the others. So there, if that is possible, then you can say that this array of oscillators is a map of frequencies, right? And in fact, you can also imagine that if you have multiple frequency components, right, f1 into e power I omega 1 t plus f2 into e power I omega 2 t, then the two corresponding frequencies will show higher response, and everybody else will have lesser response. So the map, the tonotopic map, this map of frequencies, will be like a nice map of the underlying frequencies of the input signal, right? So you can think of it as a pictorial representation of the frequency components of the input signal. Now, such a model, right, if it is generated, we are halfway through this. If it is generated, it will have nice applications in modeling many aspects of brain function, especially where sounds, auditory processing is involved. One good example is the modeling cochlea, right? And so behind the ears, behind the inner ear, you have a system called cochlea, which converts the input sounds into electrical signals. Specifically, it does some kind of a Fourier-like decomposition of the input signal, because cochlea has something called a basilar membrane. So this is like so cochlea looks like a snail with lots of folds inside that. But within this this folded, curled up region, there is a long membrane which goes into it. Membrane is surrounded by a fluid medium. So this red line is the membrane, right? So what happens here in the ear is when you hear a sound, the eardrum vibrates to it, and in the middle ear you have this malleus, incus, stapes, right? Three bones, very delicate bones, with a specialized arrangement. And the last bone stapes is attached to the kind of a doorway to the cochlea, this basilar membrane. So the bones keep shaking the end of the membrane, and therefore, in response to that, the membrane also vibrates in a very special fashion. So depending upon the input frequency, only a part of the membrane vibrates. So if it is a low frequency, if it is a low frequency, the far end of the membrane vibrates. But as you increase the frequency, the more proximal, closer ends of the membrane vibrates. So if you have multiple frequencies in the input, different parts of the membrane vibrate, thereby giving you some kind of a map of sounds or a tonotopic map. But specifically, the cochlea is not described as a tonotopic map, but it is higher up in the cortex and other brain areas, where all such maps are found. These are generally described as a tonotopic map. An excellent system, right, animal system where such maps are found is the auditory cortex of bats. Bats are, although they fly, they are mammals, that, right? So in the auditory cortex of bats, they also navigate by what is called echolocation. So they throw out sounds, right? And so when these sounds, right, land on some object and bounce off and come back to the animal, right? And based on the time delay, they can find out the distance of the target. And if there is a relative motion between the animal and the object, then the return sound will undergo a frequency change by a Doppler effect. And the change in the frequency is used to find out the relative motion, relative velocity of the between the animal and the object. So all that involves a very exquisite and sophisticated signal processing. So, in the bat's auditory system, auditory cortex, there are many areas. So this is the primary auditory cortex of the bat's auditory cortex. So, right, these are other areas. So here in the you find that the central region, which is more circular, where you have frequency on one dimension and amplitude, right, in the other dimension. Then it looks like a wristwatch basically. So the dial part of the watch has maps two quantities, frequency and the amplitude of the input, and the kind of the strap part of the watch, so this part and this part, simply models primarily frequency, because so it goes all the way from. So these units are kilohertz. Like 60 kilohertz is an important frequency because the animal transmits signals at 60 kilohertz. It looks like a very sharp distribution, right, at 60 kilohertz. And can go all the way from 10 kilohertz on one side to 100 kilohertz on the other side. Okay, so the sounds are mapped in a very interesting fashion in the primary auditory cortex. Now, bats also use frequency modulated signals. These are called chirp signals, right? Chirp. Okay, where you find actually in this case it has, if you look at the map between frequency and time, so they have it's a constant frequency up to some point and then drops. So this dropping part is what is the chirp part. That is, it has a high frequency part and then towards the end something like ooh, sorry, ooh. So you have high frequency initially followed by low frequency ending. So so therefore, in the higher areas, auditory areas of the bat, you find very complicated maps of the frequency modulated signals, right, and also constant frequency signals. Okay, so that's a very rich area that can be modeled, and we are doing some work in that area. The other area is modeling locomotor rhythms, right? Animal gaits are very interesting. So, for example, if you look at a horse, right, it has many different gait patterns. The simplest thing is just walking, right, and then you have, as it increases speed, it switches through different kinds of gait patterns, like, for example, trotting and pace and gallop and so on and so forth. Each gait pattern is associated with very specific kinds of phase relationships among all the four legs. The frequency is in this case the same. All legs are at the same frequency. But only thing is there is a subtle change in frequency when the animal turns. But otherwise, more or less, if it's running straight, the frequencies are the same for all the legs. But the rhythm keeps changing. So these pictures show how the rhythms change, right, as the animal changes its speed. Now we are trying to model these rhythms using our oscillator network and trying to drive this network out, use the network output to drive the gait of a like a legged robo. There is some preliminary work done by Shreyas here. I think Shreyas is in this class. You can talk to him more about what he is doing. So we want to put this network in a loop. So we want to put a camera on the robo, feed the camera output into an AI system. Then the output of the AI system is given to the oscillator network, which generates the gait rhythms, and then that will drive the legs of the robo. So this kind of a robo can be used to produce some simple behaviors, like just wander around without bumping into any obstacles. That's a very simple behavior. Or step on top of obstacles, right, without losing balance or without getting stuck and things like that. So there may have to use reinforcement learning concepts. But anyway, this work is also in a slightly early stages. So we have so Shreyas has done some work on this. So he's taken these gate rhythms that are published in literature, and he's training our oscillator network using these gate rhythms, which are given by some analytical formulae. So we are looking at many different network architectures to learn these gate rhythms. So what we have seen earlier is a simple oscillator network with forward connection. That's all, right? And then you look at the output and compare with the teaching signal and then give feedback, the error feedback. But when one architecture now we are exploring to model the gate rhythms is there'll be an MLP right before the oscillator network. In the output of the MLP, we'll actually calculate the frequencies of the oscillators, omegas. Okay, so that way, then depending upon the input. So input, I say, okay, produce gallop rhythm or produce trot rhythm at some frequency S1 or S2 or things like that. So different rhythms have different speeds. So the oscillators cannot have fixed frequencies. So we are training we already have some results which we train the network, the MLP, the neural network before the oscillator network to produce the values of the frequencies so that the network can produce different frequencies. Okay, and in another variation, we also have a network after the oscillator network, right? So that you can produce complex transformations, not just a linear sum of all the oscillators, and so you can produce a very complex kinds of gate rhythms. So that is one line of work, and we have some results in that. A more general version of this whole thing is develop a deep network of oscillators. Okay, so it's a deep network having many layers, and each layer has a bunch of oscillators, and all oscillators can have different frequencies, but there won't be any problem because we use power coupling, and because of that, every oscillator will get only inputs related to its own frequency. So there won't be any conflict between oscillators. So this is still, there's some final glitches with this model, and we're finalizing this. So the big picture of this whole effort is to create an alternative theory of brain function, a theory of brain. So where we try to describe all brain function in terms of oscillations. So like I was talking about this wonderful book called Rhythms of the Brain by Georgi Bazaki. So here he talks about all brain function, memory and cognition, locomotion, sleep rhythms, everything using oscillations. So we wanted to convert all that into mathematics, right, and this kind of network models using oscillator networks, right, and then explain all these phenomena: spatial navigation, sensory processing, memory, mood. Right, in mood you can have oscillations. I mean, one day you will be in a happy mode, next day you will be in a sad mode. Right, you don't even know why there is such a sudden shift. And there's a pathological condition called, bipolar disorder, where people switch between mania and depression in an uncontrolled fashion. I mean, for a couple of months they'll be in very super excited mood, and a couple of months they'll be in a depressed mood, and they have these oscillations going at a very low frequency, like running over. So how do you model that using oscillator networks, right, and so on? So we want to develop a whole alternative theory of brain function using these nonlinear oscillator networks, and also specifically want to develop a robotic system, right, which can run around, do things, inspired by a more biologically driven by a more biologically inspired system for navigation, for attentional visual search, for locomotion, and so on. Okay, so I have several students working on this. If anybody wants to do some internship or work with us on various projects described, in these slides, you are most welcome. Deepan is my PhD student coordinating all these efforts. So that completes discussion of oscillator networks, and so next class I'll start discussion of perceptron and MLP, and then we'll go to deep networks over a few classes, and I'll show you how even these simple deep networks can be used to explain a lot of observations coming from real brains. Okay, so thanks a lot, and let us meet on Monday.